Hi, and welcome back to the second video in the second lecture of Covidenomics. In the last video, we looked at SIR modelling and showed mathematically how new infections change over time. In this video, we're going to show some diagrams just to make the modelling a little bit more concrete. Hope you enjoy. We're going to have some running examples in this video. So in each case, the total population is going to be 10,000. We're going to start with one person being infected. We're going to have a gamma equals 1. In other words, our period of time here is going to be the length of time it takes for an infected person to recover or to die and to no longer be infected. In each of the cases we're going to look at here, it's going to be nice and simple in terms of our reproduction number, our initial reproduction number. So here, E is the exposure rate is 2, the probability of infection is 1, so the initial reproduction number is simply 2 times 1, which is 2. Now what we've got on this diagram is the progression of the virus in terms of new infections, that's the blue line, and total infections, which is the orange line. And you can immediately see that S-shaped curve for total infections in terms of the orange line there. Let's blow up the graph so you can see it a bit more clearly. Here again we've got total infections, new infections, both early in the epidemic or the pandemic following that exponential growth type pattern until the effect of having more and more infected people, more and more recovered people in society start to pull both of those back. Now, new infections rises, then falls back down as the disease, the virus burns itself out. Total infections rises up, then starts to flatten off as the virus burns itself out. Where is herd immunity in here? Well, remember that herd immunity threshold is where the number of new infections is constant. So it's going to be the top of this hill here, where the rate of change of new infections is equal to 0. So the herd immunity threshold occurs around period 13 in our model here. Next, we want to see how our rise in total infections changes when we have a different level of infectiousness of the virus, of the disease. So we're going to have different reproduction numbers. To make life easy, we'll keep P equals 1 in each case, but in the blue line we've got E equals 2, so the initial reproduction number is 2, and in the second one E is 1.8, so the initial reproduction number, 1.8 times 1, is 1.8. As you would expect, the lower infection rate, the infection rate of 1.8 versus 2, is going to lead to a slower rise in the total number of infections. There's going to be fewer new infections each day. And if you do the number, in fact, the maximum number of infections under the blue line, under the beta equals 2, is equal to 1,877, compared to the new infection maximum under our orange line, our beta equals 1.8. That's about 1,434 in this simple example. The second thing to note is that having a lower infection rate tends to spread the virus out over time. So the orange curve lies everywhere pushed out from the blue curve. And if you're looking for the herd immunity point, well, as before, when beta equals 2, the herd immunity occurs around here, day 13, whereas when beta is 1.8, the herd immunity gets pushed out to about day 15. And if we define the virus dying out as being the first period where the expected number of new infections is less than one person, then the virus will die out earlier with the higher infection rate. It's going to die out around about day 21 in terms of the beta equals 2 virus, and in fact it hasn't quite died out here. It dies out about day 25 with beta equals 1.8. And if we look at the total number of people, or the total percentage of the population who have contracted the virus at some stage before the virus dies out, then we're looking at about 87% of the population when beta is 2, and only about 80% of the population when beta is 1.8. From both a population and a government policy perspective, it's clearly much better to have the low beta. Think about that. If a certain percentage of a number of people who become infected die, then clearly you're going to have a lower death rate or a lower number of deaths under the beta is 1.8 versus the beta is 2 virus. And secondly, if you're worried about overwhelming the health system, well, that's going to depend on the number of new infections. Because the number of new infections is always lower for the less contagious virus, then again, you've got less probability of overwhelming the health system. So it's pretty good to have a lower rate of infection. And just to illustrate that this pattern continues, here we've got a grey line. This grey line involves an E of 1.2, a P of 1, so a beta or an initial reproduction number of only 1.2. And you'll see here the virus struggles to get off the ground and dies out well and truly before you've had even 40% of the population infected. What we've had during COVID-19 with a number of countries is restrictions put in place that have reduced the level of infection, but then these restrictions have been removed and the virus has taken off again. We've seen that, for example, in particular in the US. And it's sometimes said, well, then we wasted the restrictions, that we haven't gained anything by having a restriction. Well, this little example here shows that that's not quite correct. Again, we have in blue our base case where beta is equal to 2 right through the pandemic. In the orange, though, we've got a situation where initially we start off with a low beta. So imagine there's some sort of restriction in place on movement, there's a lockdown or something like that. We're going to describe them a bit in more detail later on, but something that's reduced that E, that exposure rate down, and got it down to only 1.2. However, at the beginning of period 39, the restriction gets removed, and we return to a situation where E is equal to 2. So have we wasted the restriction? Do we just simply end up with the same number of deaths, the same number of infections as if we hadn't had the infection? Well, the answer is clearly no, as you can see here. When the restriction is taken off and the reproduction rate of the virus goes up, sure enough, we end up getting back to some exponential growth in the virus, but it never quite gets up to the same level of infections as if the restriction had never been put in place. Why? Because the population has changed. When the virus gets released, for want of a better word, in period 39, and that infection rate goes back up to 2, you've already got a population which has had a significant number of people who have had the virus and are no longer able to contract it again. And that means that you're starting off with a population in a sense that already has some level of immunity. So even though the level of infection goes back up again, because you're not dealing with a population where everyone's susceptible, you're dealing with a population where some people have already had the virus, it never quite accelerates at the same rate as it would do if you didn't have the restriction in place. So the restriction does have that benefit. Notice, however, that some patience is needed for this, because the restriction, as we noted before, pushes the whole process of the virus infecting and eventually dying out. It pushes it out over time. So when you have those restrictions removed, yes, you get this second wave, as it's sometimes called, and it seems like you've wasted time, or no, you haven't. But it does in some ways depend on what the objective is. If the objective was, hey, let's get this thing over and done with, then the restriction and then removing it may not be the right policy. Let's add some more detail to our base example. So remember, population of 10,000, one person starts off being infected, E equals 2, P equals 1, so beta, the initial reproduction rate is 2. Let's assume that 30% of infections become critical. So they're going to be the number of people who require intensive care in a hospital. And let's assume that 2% of infections lead to death. And we've got, as before, the total number of infections in the blue. We've got critical in the orange, and somewhere down there in grey is the number of deaths, but that's not very useful. So let's duck over here where we've got rid of the total number of infections, and we're just concentrating on the number of people who are critical, who end up in the emergency department, in critical care, and the deaths, the cumulative deaths, given here by the orange. And these are pretty much as expected. The number of critical infections at any point of time just follows the number of infections at any point in time in that hill-type pattern. And we have this S-shaped death curve, which simply follows the S-shaped total infection curve. In this last part of the video, we're going to look at a government policy you may have heard of called test and trace. The idea behind test and trace is that, let's say someone's showing some symptoms of COVID-19. They come in and they're tested. They're positive. You then trace back who they've been in contact with because they may have passed the virus on to those people. You can then find those people, you trace them, you find them, you test them, you potentially isolate them whilst their test results are coming back. And that means that if they are positive, if they have been infected, they can't infect anyone else. This idea of test and trace is being widely used. It sometimes has technology involved. So, for example, in South Korea, it's been used very effectively through a range of devices, such as using closed-circuit cameras, being able to use location information from individuals' phones, and so on. In most countries, there's issues with privacy and access to that data. So there's been either more subtle solutions, such as the app that we have in Australia, which doesn't trace location data. It's simply phones pinging other phones, and that data is only used if the owner of one of the phones is found to be infected. Or what's also used everywhere in addition to any electronic processes is the physical tracing of people. Who have you been in contact with? Where have you been? Tell us their names. We'll trace them down. We'll go and have them tested. So what's that do to our infection? Well, here in blue we have our normal infection, just with a beta equals 2. The orange curve, it's actually going to start off being the same infection, but on the fourth period, from day 4, we're going to introduce test and trace. And test and trace is going to catch 25% of the infected people with a 1-day lag. How can we think about that? Well, you can think that somebody comes in with an infection with some symptoms, they get tested, yes, they're positive, you go and trace, and you're able to trace down everybody that they've been in contact with and stop them infecting other people. However, only 25% of people have the symptoms, come in and get tested. So you're only 25% effective at using test and trace to stop various paths of virus from continuing. But still, as you can see from this diagram, that makes a big difference. So the test and trace, when it comes in, really slows down the progress of the virus. And you'll see here that instead of having around 87% of the population infected by the time the disease dies out, you're really looking at more like 20-25% of the population being infected. And again, you can see that big change due to test and trace. In this diagram, remember we had 30% of people who are infected become critical and need intensive care in hospital. Blue again is with no test and trace. The orange is with that test and trace. And so if you're thinking about overwhelming or the potential for the virus to overwhelm the hospital system, and you've, say, got 300 intensive care beds, then without test and trace, you're turning football stadiums into hospitals. With test and trace, you're able to stay under that critical threshold. And this diagram is a case where we've got test and trace being highly effective, so catching 75% of all of that second generation of infections before they can infect anyone else. And notice now you've got the virus essentially dying out before even 50 people out of our 10,000 are infected. So this would be a really effective intervention for government. Whilst the curve here is for test and trace, really what I want to represent here is what's occurred in some countries such as New Zealand, such as Taiwan, such as Vietnam, and to some degree in Australia, where a combination of government policies came down very hard on the virus early on and meant that the virus really didn't take off, that the overall infection and death rates remained very, very small. That's been fantastic for those countries, except remember that we had the graph before about what happens if you have a restriction, then take it off, and the virus takes off again. And notice the virus wasn't as virulent as if it was starting from scratch, because you had some people who had recovered in the population, so it couldn't spread quite as fast. Well, the problem here is that if you've been really, really successful, like Vietnam, New Zealand, Australia, in crushing that virus early on through government policy, and then you let the policy relax, and there are still infected people out there, or overseas travellers can bring the infection back in, then the virus is going to take off as if it's new, because there's hardly anyone who's in that recovered category in the population. Now, as I'm presenting this video, we're in Victoria, and Victoria has suffered exactly this problem. So what happened was Victoria, as part of Australia, was able to crush the virus very quickly. It started easing up on the social distancing restrictions, allowed more businesses to open, and so on. What ended up happening, however, was that there were some overseas visitors, there were people in isolation who'd come in from overseas, but the quarantine wasn't quite as good as it should have been, and the infection got out. And once it got out, it was basically starting from scratch again. So what we've seen in the last couple of weeks in Victoria, in Australia, is we've seen the virus start to grow at an exponential rate again. The rate of new infections doubling about every 2 or 3 days. What's been the result? Well, the government tried test and trace, but the rate of infections was such that it simply didn't have the manpower to do all of the tracing. It tried locking down some high-rise buildings where the infection was running through those buildings, tried locking them down to stop it from spreading outside the buildings, but it was already a bit too late. So we've just gone back into lockdown again, which means not meant to leave home except for getting supplies, for health reasons. If you're essential in terms of your work, that's pretty much it. For another 6 weeks. So what we've got on this graph is, in a sense, the nirvana, or what appears like nirvana in terms of public policy. Crush the virus before it can take off. But that only works if it can't get back in, which means you have to keep your borders closed, potentially until there is a vaccine and the rest of the world becomes vaccinated. Thanks for listening. Next time, we're going to look at some of the economics that undermines this SIR modelling. Talk then.